now that we understand what momentum is and we understand the conservation of momentum, we can look in a little bit more detail in collisions and ways of analyzing them. So just some definitions. Two types of collisions we'll look at: elastic and inelastic. So elastic collision just means both momentum and kinetic energy are conserved. And it's just like it sounds like. You can almost picture like two tennis balls or something like that with going. There's no damage to either, no permanent damage to either of them. Versus an inelastic collision, which is momentum is conserved, because as I said, when we looked and studied momentum, it is always conserved, even if energy is not, right? Which makes it really helpful. But for an inelastic collision, kinetic energy is not conserved. And we often, just to simplify things, we like to look at the perfect cases, and that's mainly just for analyses. And so questions we do will generally be one of these two situations, where we'll look at perfectly elastic, which means the collision is an ideal collision in which 100% of the kinetic energy is conserved. Obviously, in the real world, that's never going to be perfectly the case. I said even something like two tennis balls or whatnot, right? There's going to be just some heating while they're deforming and coming apart, but it's a pretty good assumption, right? It's like assuming G is constant or things like that. Like, they're pretty good approximations. They give you really good values. The other side of this is we can look at collisions that are perfectly inelastic. And these are collisions in an ideal collision in which two objects stick together, so they have the same final velocity, right? So let's look at this, or let's see what this looks like as an example. I've got one written here. So we have a 1 kilogram mass traveling 1 meter per second. You can let that be the positive direction. It's going to collide with a second 1 kilogram mass, which is at rest. So we want to determine the final velocity and kinetic energy of the system before and after the collision. And we want to consider case A, right, an inelastic collision, and case B, an elastic collision. And if you can, even get the final velocities, if you can, of both of them. So I feel like this is an important one to try, right? To just have a go at it yourself, see if you can use these equations and come up with something. Poof. You can see I just did the whole thing here. So yeah, we have a 1 kilogram mass and a second 1 kilogram mass, and the first one is traveling 1 meter per second. So pretty straightforward situation, and the one collides into each other. So first, let's look at inelastic. So if we look at an inelastic collision, before the collision, right, we have just the 1 kilogram mass traveling at 1 meter per second. So the momentum before is just the momentum of, or I'm using initial here, an I for initial and an F for final. So the initial momentum is just the momentum of A, because B is stationary. And it's 1 kilogram times 1 meter per second, so 1. The kinetic energy before is just the kinetic energy of mass A, which is 1/2 times 1, its mass, times its velocity squared, and 1 squared is 1, so it's just a half, or 0.5. And then after, remember, perfectly inelastic collision means they stick together. So now we have basically now we have a 2 kilogram mass traveling, right? And we're not really sure what right? So we can use momentum. We can say, well, the momentum before has to equal the momentum after, right? And the momentum after is just, you add the two masses together. So we have a 2 kilogram mass traveling at some velocity, and that has to equal the momentum before, which we just figured out up here is 1. So that has to equal 1. MA plus MB, they're both 1, so that's 2. And that means the final velocity of the two of them stuck together has to be 0.5. We can use that now to calculate the kinetic energy after. And you might even think, like, well, we have 2 kilograms now traveling, right? Not just 1. So might it even be more? But nope. The kinetic energy after 1/2 times the combined mass, because it's 2 kilograms now, but So the 1/2 and the 2 basically cancel each other, and you're left with 0.5 squared, which is 0.25. So actually, if you compare the kinetic energy before and after, right, it's half. Right? So we definitely lost some kinetic energy when we have an inelastic collision. Get rid of that. Now consider the other case where this is an elastic collision, and this actually mathematically is a bit more challenging, or there's a few more steps. Now, before we already calculated these, so of course we can use the same values. We already know the momentum before is 1, the kinetic energy of the system before is 1, but now it's elastic, so now we know that has to be conserved. The challenge is they're not stuck together anymore, right? So we have to know both final velocity. So if we just look at momentum, right, we can look at that equation, and so this here is basically just saying momentum after, or the final momentum, must equal 1 because that was the momentum before the collision, right? And then since these masses are both 1, right, I just put it like putting 1 in front of VFA, or V final A and V final B is kind of unnecessary, so I just basically put in those numbers, and that reduces to this equation here. V final A plus V final B is 1, which I rearranged for V final B just because I know I'm going to need it later. You could arrange it for either one, it doesn't matter. And that's as far as you can go with momentum. You can't figure out each one from this, right? Because there's 2 unknowns and only 1 equation. So for that, you actually need to use energy. And if you write out that equation, right, we know the kinetic energy after has to equal before, which is 0.5 or 1/2, same thing. And then just putting in the numbers. Note that 1/2 is in every term, so you basically can cancel those out, right? And again, MA and MB are just 1, so you can basically reduce that equation to just V final squared plus, or V final A squared plus V final B squared equals 1. Then we can take that equation and substitute it in. So that becomes, so V final B becomes 1 minus V final A squared. And I'm oh, I actually wrote that incorrectly, didn't I? The squared would be here, because we're just substituting in this part of the equation, which is just 1 minus V final A. And so when we put that in there, that whole thing would get squared, which I did actually do below it, so that was just a silly oversight. So when you work out, 1 minus V final A squared, you get this right here, right? And you can check that, or if you want to, you can write 1 minus V final A times the same bracket, and then that's just FOIL. Just multiply those 2 binomials. You should get this. And then now you've got 1 equation with 1 unknown. You can reduce it. I see that there's a 1 on both sides, so that's what's crossed out there. And that leaves me with 2 V final A squared, because I add that one and that one. And then this is kind of a quadratic, but there's no constant here, so I just factor out one of the V final A's, and or I guess I don't even need to do that, do I? Sorry, I did that wrong. Sorry, that's where I messed up. That shouldn't be squared. This second term here is this same term there. So minus 2 V final A. I guess that's one reason to be very careful with your keeping squareds and things that don't have squares separate. Again, now basically I can divide both sides of this equation by 2, which cancels them out. Because 0 divided by 2 is still 0. And it reduces that. Then I can actually factor out a V final A, leaving me with V final A minus 1 equals 0. And so that gives me technically 2 solutions for V final A. It gives me 0, because that would be this one here, and positive 1. And then I got to look at, well, what does that really correspond to? So 0, right, would basically mean it stops in its tracks, right? and then v final b would become 1, right? If I go back to this equation here, v final b would be 1 minus 0, which would be 1. And so neat that v final b would be the same as the speed that v1 had, right? So v1 was traveling along at 1 meter per second. It hits a mass that's the same as it, and mass A completely stops and mass B takes off with that velocity. That's what that effectively would mean. Mathematically, 1 is also a solution, and that would just correspond to it goes right through VB, but that's not really possible, right? So that one here then is, this one here is inadmissible. So I guess you could write it that way, that you could say 0 or 1, and we could say this one here is inadmissible. And so it's 0. And that means that V final 2 and that's what you end up with, right? Which is, again, kind of a neat situation. I went and even got this picture because if you've seen this, that's exactly what's happening here. It's just happening over a series, right? This ball here has some speed. When it hits that one, it transfers all of it, because they're all the same mass, it transfers all of its momentum to that one, which then transfers all of its momentum to that one, which transfers to that one, and then this one goes off with that same speed, and the rest of it all just sits there stationary. So that's what you're seeing when you look at this device here, which I believe is called Newton's cradle. And so that's where we get that phenomenon from. Kind of neat, maybe. Now you can explain that. So I made this example actually originally, and then I made the previous example after, because I thought putting those concrete numbers might be a little nicer and something you could do a little more quickly, whereas this as a first question is pretty tough. You've got to just keep the variables as variables, right? We're looking at the maximum velocity a very massive object can give a stationary, very light object. And in this case, just as sort of a percentage of the more massive velocity. So again, imagine, or just to draw this, not again, I haven't said anything yet. What am I talking about? So imagine we've got some big M, right? Something like a wrecking ball or something here, right? And it is going at some speed here. We could call this V of the big M initial. Or I guess I've been writing it the other way, haven't I? I've been saying V initial of big M. And it's going to bump into some little m. And in this case, V initial of little m is 0. Not going anywhere. And so, again, think of it like this is a wrecking ball. We'll let this be an elastic collision. So picture like a M, the little m is maybe a golf ball or something, right? And just try to think to yourself, well, what is the maximum? And I don't know what this velocity here is, but it could be any number. It could be, 10 meters per second. I don't know. What's the maximum velocity do you think that M2 or the little m could take off with in an elastic collision? A first thing you might even think about is, well, what should be the final velocity of big M, right, of the wrecking ball? Should it really be affected at all by this tiny little golf ball? I would say no, and that should be consistent with kind of your everyday experience, just looking at things and trying to understand them, right? Of course, if you have a giant wrecking ball and it hits something like a little golf ball, it's not going to be affected. You wouldn't notice any effect on it. So then we really have to think, well, yeah, what would that final velocity be, right? We're looking at V final of little m. What would that, right? And we know the big M, okay, so that's basically unchanged. How could we do this? So We do the same thing as before. We can look at momentum, and we can look at kinetic energy. Right? And so the equation for momentum, right, would just be, I guess since I'm writing them this way, we look at the momentum before equals the momentum after. So that would be big M V initial big M plus little m V initial of little m. And we know that this here is going to be 0. And that's going to equal big M times the final velocity of big M plus little m times the final velocity of little m. We can have that equation. We can also have the kinetic energy equation, which is somewhat similar, which will be 1/2 big M V initial of big M squared plus 1/2 times little m times V initial of little m squared. And we know that's equal to 0, so once again this whole thing will also equal 0, and that will equal 1/2 big M times V final of big M squared plus 1/2 little m V final of little m squared. Then let's kind of number these or whatever, right? We could look at this and say, okay, this is equation 1, and this here is equation 2. We've got almost everything on one. Like if you look at equation 1, and maybe I need a little bit more space here. Sorry. Let me just move this down a tiny bit. If we look at equation 1, what I might do is say, look, I've got big M. Like on the other side, I really just have this one term. So what I can do is I can just divide through by big M every term. And then here they cancel, here they cancel. And on the left side of this, I'm left with just V initial, right? And so from equation 1, I'm using the wrong. I can say V initial of big M is equal to V final of big M plus, in this case, it's going to be kind of a ratio M over big M of V final of little m. And just because I'm probably going to want V final later, if you want, you can basically move this term here over to the other side, right? And so you can make, which leaves V final of big M would just equal V initial of big M minus little m over big M times V final of little m. Just to rearrange that so that I can then, and if you want, I can even call that equation 3. And then I can take equation 3 and if you look back at equation 2, all right, so I might even do a little bit of work on this one too, just before I bring it down. Again, this whole one term canceled there, but I've also got, for the 3 terms I've got left, I've got a half everywhere. And so yeah, that would be reasonably good there. So if I look at the first term in equation 2, it's big M on the left side, V initial of big M squared, and that all equals big M V final of big M squared, this term here, but that's what I just solved for, right, with equation 3. So I can actually take that and find it. The initial of big M minus little m over big M, V final of little m squared, and then so that's where I left off right here, and so then I just have the last term plus little m V final of little m squared. Now note too, ultimately what I'm trying to do here is I want to get equations that will give me V final of little m, right? That's ultimately what I'm trying to figure out here. I've got this little mass here, so having an equation that has V final of little m, and it's basically in terms of the two masses and in terms of the initial of big M, right, which is the initial velocity of the only one that's moving. So now it's just a little bit of work to sort of isolate V final of little m. Right? I would divide everything through here by big M, which kind of helps me out with that. And then that leaves me with V initial big M squared equals, now this term I've got to actually square and work out the bracket there. So that'll give me the first term squared, which is V initial of big M squared. And then the first term times the second term times 2, if you're just working out a binomial like that that's squared. So minus 2 times V initial of big M times by little m over big M times by V final of little m. And then the last term squared, which would become positive because you're squaring it. Little m over big M. And I don't know, I'll just write it like that, squared, and V final of little m squared. All plus little m over big M and V final of little m squared. So this does seem to be a little bit more of kind of a math exercise, but I think it'll clean up a little bit right now. I've got V initial, if you look on the left side, I've got just that one term, V initial of big M squared, and on the other side I've got the same thing, right? That's the very first term here, the initial of big M squared. So that just gives me 0 on that side. I've got this term, little m over big M, kind of everywhere, right? So now that this whole thing would just equal 0 because I've subtracted it from both sides, I can basically divide everything through by this term here, and I can cancel it there. I can cancel the squared, and I can cancel it here as well. So it kind of ends up everywhere. And I think that kind of helps me out pretty well. I'll rewrite it just because it's getting a little bit messy. So that leaves me with minus 2 V initial of big M times V final of little m plus V final of little m squared. Oh, sorry. That's the one where I actually needed it. Little m over big M times that plus V final of little m squared. That being, like I said, the one that I actually want, V final of little m. And that actually does show up in all 3 of these terms, right? I've got V final of little m, so I can kind of cancel that, and I can cancel the squared, and I can cancel the squared here. So I can add this term to both sides, which leaves me with 2 v initial of big M, if I move that to the other side, and then I'm just left with these two terms here, so I can factor that out. I can say that equals v final of little m times little m over m plus 1. And then I can divide both sides by what I've got in the bracket there to isolate v final of little m, which tells me v final of little m equals 2 v initial of big M divided by m over big M plus 1. You could probably multiply through by big M or something here to sort of get that, or multiply the top and bottom by big M, and that might give you a little bit of another way to look at this. But I feel like all that math sort of culminates in something that we can actually look at and now appreciate, right? So we've got an equation here, and the challenge with this now is, okay, look at this thing and ask yourself, okay, what happens if big M is really, 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 really big, right? Like millions and millions of kilograms, and little m is itty bitty, like not even 1 kilogram, right? It's like a gram, or it's almost nothing. What happens in this equation to this term right here, right? If big M is really big and little m is itty bitty, right, what does this term here almost equal? Yeah, and that's really like, we're getting to, limits or something like that. But yeah, basically you're saying this term is going to approach 0, right? It's going to become infinitesimal as big M is really, really big and little m is really, really small, right? The more, if you consider that like the most dramatic case, this is essentially 0, right? And in which case, all you've got is 1 in the denominator, and so v final of little m is just equal to twice whatever v initial of big M is, right? And so that tells you that is the maximum possible velocity you could get, right? If you've got that giant wrecking ball and you've got that little tiny golf ball, the maximum velocity you're going to get out of it is just twice whatever v1 is of the big one, right? And obviously we could do a similar analysis like this. We won't, but we could go through this and look at, well, what is v final of the big mass, right? And you would see that, well, yeah, that's basically unchanged, right, as this ratio here approaches 0. But yeah, we can state that as well. We can see here that as, well, it doesn't really matter, right? So as little m over big M approaches 0, I just use the arrow to sort of say approaches, v final of little m approaches to v initial of big M. And I would say that that's all there is to it, but I feel I should say it more like that's all there is to it. For where you are right now, right, if you've got an elastic collision, you've got stuff like this to do, right? We kind of did it a little bit over here. It was a lot easier. It was a lot nicer numbers. And now we're seeing, okay, if we want to be really general, this is probably the most difficult way to do it, where you've got to just leave everything as variable and work your way through it. It ends up just being a lot of math. But as I think I said at the beginning of this course, I mean, as you get into more and more physics, it becomes very math heavy, right? And then it's just sort of seeing it in the real world that, oh, well, the math actually works, though. And to save you all the time and trouble, And I'm definitely not going to derive these any more than this. You can see that is essentially one of the derivations here. I gave these to you on the next page. I would say you're really welcome, but I suppose you're welcome for not spending all of a class just doing that. I think you can find them in a textbook or most textbooks anyway. And so if you have a head-on, and again, we're only looking in one dimension, but if there's multiple dimensions, just look at them independently. This would give you those equations right out of the box here. And what might help you is if V initial of mass B, and it's up to you to say which one is A, which one is B most of the time, so it doesn't really matter. But if that's equal to 0, right, i.e. mass 2 is at rest, then it just reduces to these. And you can see the second one for VB, that's what we just found, right? Basically, all I did was here I was using big M and little m, but like I said, you could multiply through by big M, and you could see you'd have a big M on the top, and that 1 would become big M, and that is essentially what is written here for V final of B if mass 2 is at rest. And if you wanted to, you could just look at this equation here. Remember, I made the claim that the big mass would be pretty much unaffected. And so you can consider, well, yeah, what happens to this equation if mass B is essentially 0 compared to mass A? You can see, well, yeah, these two terms cancel. Mass A over mass A is 1. So yeah, V final of mass A would basically just be V initial of mass A, right? It approaches being completely unaffected. And here's the more general if it's not. But as I mentioned before, with one thing, you can always change your perspective and just use these. You don't have to, but it might be more helpful, right? Like if, for example, you had mass A moving at 10 meters per second and you had mass B moving at 5 meters per second, right, in that direction, you could always just change your reference frame and say, look, as far as mass B is concerned, right, its mass is, or not its mass, its velocity is 0. And A is approaching it at 5. And you could do your whole analysis with those numbers, right, and use these equations. And then after you get your final velocities, you could just add the 5 back to the final numbers, and everything would work out as if you would use these monstrosities up here. So just a tip, because here to help.